lecture here. Okay, so I was told to tell you about the replica method and its application in disordered systems, and of course, in order to understand computational problems. And before I do that, so my goal is to do that on concrete examples where I will do calculation on blackboards on so I will start with very simple examples which can be solved without replicas so that you see the exact solution, and then we will actually solve again the same model with replicas so you can really understand how that works. But before I do that, I think it could be of interest to have a broad introduction just to give you the feelings of what replicas are about. So I'm a little bit on the tightrope here because I know that some of you are already experts in replicas and other ones here I've never heard about them or very little. So I don't know whether I will try to satisfy both categories of people or maybe everybody will be unsatisfied or dissatisfied at the end. So I just would like to say a few things with a short historical introduction. It's just a 5 slides, so it will be brief. But I think what Lenka told us, and also Mark this morning, about how a lot of things actually already emerged in the 80s in statistical physics with a lot of interdisciplinary application that was finally recognized by the Swedish Academy of Science a few months ago, when the Nobel Prize was awarded to Giorgio Parisi for half of the Nobel Prize. And I just cite here on the right side the declaration by the Academy, and you see that so it's clearly stated that everything took place at the beginning of the 80s, as we know, but then of course that expanded over the 90s and more recent years. And so his discoveries and the discoveries made by the people actually who contributed a lot are among the most important contributions to the theory of systems. They make it possible to understand and describe many different and apparently entirely random materials and phenomena, not only in physics, but also in other very different areas, such as mathematics, biology, neuroscience, and machine learning. So I would like to spend just a few slides on the historical aspects in physics, how this was possible, and the techniques which was used, which was essentially replicas at that time, and later on the cavity that Mark already told us about, and is going to tell more in the next days. And essentially what I would like to do today is, in the first part, is to give a short historical background, then give some kind of flavor of the replica approach, what it means, how it is defined and what it means, try to give you some ideas. I'm not expecting you to understand everything about the replicas at this point, but then that should come at the end of the second lecture, right? Because then I will look at a very simple, exactly solvable models that we will solve today without replicas, and tomorrow with replicas. It's more lengthy, but we'll see that we can really look at very detailed detailed properties of the model and how we can recover everything. And then in the next lectures, I would like to go to more interesting or maybe more sophisticated application to supervised and unsupervised problems. And with some connections, I would like to strengthen maybe on the last lecture with the ideas of representations which are not existing only in machine learning, but also are very important in neuroscience, and there are deep connections in the models and the approaches. I would like to say a few words about that. So just a few slides about the history. So the history of the replica approach and how it was actually applied, and it came to very big success, is it started with magnetic materials. So magnetic materials, they are materials where you have electrons which actually carry spins, and these spins can actually define magnetic moments. And here you see a photo, for instance, of a magnetic materials. You see domains. So the typical size here is a few tenths of micrometers, so very tiny domains. And a simple picture is within the domains, all the magnetic moments carried out by the electronic spins are aligned in the same direction. So you see a representation, a cartoon of this here. And within different, if you look at two different domains, there are completely unrelated orientations. And as you decrease the temperature, the size of these domains is just getting bigger and bigger. This is related to the correlation length side Mark was mentioning before. And if you go to low enough temperature, then you get a single domain which invades everything, and then you get a fully magnetized material, which is a permanent magnet, for instance, if its low temperature is comparable to the room temperature. And this is the magnet you know. Okay, so what kind of mathematical description can we have for this? So the mathematical description known under the name of Ising or Heisenberg models is the following. So suppose the magnetic moments, they are just some vectors. So I will assume that my material is a crystal. So it's living, let's say, so I do it in 2D here because I'm very bad at drawing, but you should imagine it's a 3D material. I will show you some examples of lattice in 1 minute. And on each side I, here, you will have a magnetic moment. Here, this is J, which I describe by some vector, Si, Sj, and so on. And for simplicity, I will assume that these vectors are, have unit norms, and they have the same dimension as my lattice. So for instance, 2D here on the blackboard. So now we describe the probability, the joint probability distribution of all these vectors here by this distribution here. So it's up to some normalization factor, the exponential of this following term. So I take all pairs of sites which are next to each other on the lattice. So for instance, this one and this one. Okay, and then I compute the dot product, the scalar product between the two attached vectors here. So that's the Si dot Sj. And I will sum this on all pairs, right? And the probability is just proportional to the exponential of this sum times some proportionality coefficient, which is J, which is called the interaction exchange, okay, the interaction constant, and divided by T, which is the temperature. Okay, so this is a very classical model in statistical physics. And you see exactly what it's going to do. If you are at very low temperature, let's say, suppose you start with very high temperature, T is very high. So essentially what is inside the exponential is vanishing, which means that all these configuration of unit vectors are equally likely. So they can just rotate on each side independently from each other. While if you decrease the temperature, if J is positive, for instance, then they will have a tendency to align along each other because the dot product is maximal when they point in the same direction. So this is what you see here in this cartoon. At high temperature, you would expect a typical configuration to be like that. At low temperature, if J is positive, it should be something like that. They all point towards one direction, which here is the vertical axis, but it could be anything. It doesn't change, by a global rotation. And now if you do low temperature, J is negative, then what is going to happen is that nearest neighbors are going to anti-align, because this is how you would get a dot product here, which is minimal, which is -1 when they are just in the opposite direction, and you multiply by a negative constant. So it's a way you make this probability maximal, right? So it's very nice. It's very nice, except that it's nice only if I am on such a lattice where you see some kind of square grid here, because then my constraint is always compatible. I start with one direction, for instance, the up direction for this spin. The next one is down because it's a neighbor. This one is up because it's a neighbor of the top one. And then when I close my loop, I don't have any contradiction. I'm very happy with that, right? But as soon as you go to more complex lattice, or let's say different lattices, then of course you get into troubles. So for instance, if your lattice is not a square grid again anymore, but it's a triangular lattice, then you get into troubles, because if you try to do some greedy search of the best configuration of the spin, so for instance, you start with this one to the top, this one will be down, and that one, cannot be aligned up or down, so you get into troubles, right? So you have to solve the whole global optimization problem to find the best configuration of the orientation of the spins, which minimizes this energy or maximizes the probability, which is the same thing. And it can be actually quite complex. So here's an example of a material, antiferromantic material, 3D lattice, pyrochlor lattice, where actually you have a lot of small arrows pointing in direction, and this is actually the best configuration you can think of. But you can reverse the configuration of the arrows locally and propagate this changing here, so that means there are many, many configurations which actually achieve exactly the same probability. So as soon as you don't have a simple lattice like that, but you get something which is called frustration, because actually the cycles here are of odd lengths and not even lengths, then you get this very complicated best configuration, and there might be many of them. So that was the situation up to the beginning of the 70s, and in the 70s, actually, even more complex material came on, and this is the only my last material slide. is what people call spin glass. So in spin glasses, the situation is even worse than that. Here we still have a periodic lattice, but this periodic lattice is lost here. So essentially what happens is that the spins are carried by some impurities, some specific atoms, which are more or less randomly scattered in the material. And they will carry momentum, these magnetic moments. But the interaction between the different spins, this J coefficient I have mentioned before, will depend on the distance between the spins, right? And it depends in the distance in a very complicated way, which changes sign depending on the distance. So this is the interaction here as a function of a distance. So that means that, and this typical distance along which this is changing sign is a few tenths of nanometers. Okay, so it's a very short distance. So that means if you look at your material, you have spins which are positioned in a totally random way, and depending on the distance, the interaction can be positive or negative. Okay? And now you ask what is the configuration with the highest probability. So you see the big change between the problem I mentioned here and this problem is that now the interaction J depends on the pair of spins. It's a Jij, right? And it can be positive or negative. Yes?
It's still a pairwise interaction.
It's still a pairwise interaction here, yes. Yes. Okay, so now the problem is that you are facing is that you would like to understand what is the nature of this distribution. Okay, so you have n vectors that you would like to, and you like, for instance, to understand what is going on at low temperature. And it's a very complicated problem. And this is really the archetypal problem we are dealing with, and I will deal with in the next 4 lectures. Okay, so let me now, after this introduction, go to the more precise definition of what we are looking at. So in all the problems I will consider, there will be 2 types of variables. So the variables which I will call quenched random variables. So in the examples I showed, they were the interaction between the spins. So going back to the material here. So what is going on here, and it's very crucial, is that the position of these spins, they are obtained when the material is actually built, right? So they are essentially random, and they don't change as you study experimentally this sample. What can change are the orientation of these spins, because the dynamics of these spins is much faster than the dynamics of motion of diffusion of the position of the atoms which carry the spins, right? So you really have 2 kinds of disorder, and this is the point of this slide. You have the disorder which is quenched. So there are random variables which are drawn once for all at the beginning of the definition of the problem, and here they will be the matrix of interaction Jij. So they are drawn at random, and it will, I mean, there will be a specific distribution we'll have to actually make clear when we study a specific problem. So in my case here of spin glasses, they can be positive or negative. And they are quenched. That means they do not vary for a given system of sample. Okay, so we fix them forever. And then we have the other variables, which in my case are the spins, so these vectors, unit norms, which are drawn from a distribution which is conditioned to the value of the quenched variables. So in the example I gave you here, that's just a joint distribution of these different spins, which is given by this distribution here. So it's a very tough problem, because if you want to study this distribution, you immediately see that the outcome should depend on Jij, right? If you ask what is the best configuration with the highest probability, it will depend on Jij. It's a very complicated thing to determine. Yet some properties may not depend too much on Jij, especially in the large psi limit, and we'll see that also. Okay, so one example which was very important of such a problem is called the Sharanton-Kirkpatrick model. I'm sure that many of you have already heard about it, but maybe not everybody, I guess. So it's an example where you have exactly this model, but you simplify in 2 ways. You simplify first, instead of having vectors here, you take just, let's say, 1-dimensional vectors, so of unit norm, which means numbers which are plus or minus 1. So the SI are plus or minus 1. And you also simplify the distribution of the Jij. So in principle, in a reasonable material, the position of the spins here are random. But since the interaction depend on the distance, the different interaction here, Jij, which depends on relative distances, will not be, they will be random but not independent from each other. If you, okay, you will have correlation. So in the Sharanton-Kirkpatrick model, this is completely forgotten, and you just assume, for instance, that the Jij are drawn independently from each other from a Gaussian distribution with a fixed variance and zero mean, for instance. Okay, so it's a model which was historically very important because it led to many discoveries and very important physics. Okay, so this dual aspect of random variables is all over the place, and let me give you two examples which are more related to what you are interested in. So in supervised learning, and this was already explained by Mark earlier this morning, suppose you have you would like to associate some inputs x mu to some outputs y mu, where mu is the index of your data point. And you would like to do that with a paramagnetic model. So y is a function of x and some parameters, theta. Then your quench variables are the set of data, x mu, y mu, all the pairs. And your thermal variables, the one that actually you will try to optimize over here, are all your parameters, I mean, inside this big theta set, right? So in fact, the analogy can be quite deep. If I consider the loss, which is a measure of how bad my guess over the parameters theta is doing, that's a measure of a square discrepancy between the desired output and the one computed by my model, then I may think that, for instance, I would like to distribute my theta parameters according to some distribution, which is controlled by some effective temperature. It's not a physical one, it's just a fictitious one, exponential minus the loss over t, sorry. And that defines here a probability distribution for theta conditioned to the data set. So stochastic gradient descent is not going to realize exactly that, but I mean, it's a kind of reasonable approximation where as you decrease the temperature, which is a learning temperature, then you get closer and closer to the best value of theta. And depending on your data points, this landscape of theta can be quite complicated. Okay, so another example which is similar to that in the case of unsupervised learning. So now suppose you have only a set of inputs, you don't have any outputs, so just data points here. And you would like to learn a model from this data. So I have a parametric model which is defined again by some probability of x conditioned to theta with some p prior of theta. Then I have two kinds of quench and thermal variable depending on whether I'm considering the training or the sampling regime. Here I'm talking about unsupervised learning of a generative model. Once the training is done, I can use it to generate new data. So during the training, I will look at the posterior distribution of theta given my data, which is due to Bayes' rule, just is proportional to probability over prior times the product over the data points of p of x mu theta, the likelihood. And very clearly, if I want to maximize this over theta, you see that the thermal variables are going to be the theta and the quench variables are d, the data. That's the training phase, and it's very similar to the supervised learning example I was giving on the last slide, right? It's exactly the same. But now suppose you have done the training, so you were able to actually find maybe the best theta, maximizing this. Okay. Then you use your model to generate new data points. It can be very useful in some application. Then what you will do is that you will consider the probability of x given, for instance, theta map, which is the maximum a posteriori estimator of theta. And this is the quench variable now. It's very involved. It depends in a very involved way, in a very complicated way on the data, but it's quenched. It doesn't change anymore when you do sampling, right? And your thermal variable is this one. So depending on what you are doing, the variables don't play the same role. Okay? So I'm going quite fast here, but I think they are not very complicated notions, right? It's just kind of to refresh maybe a few definitions. Okay, so now I would like to give you a flavor of the replica method for those of you who have never heard about it or have heard very little about it. So since we have two kinds of random variables, the quench and the thermal one, we can do two kinds of expectations, right? So suppose, for instance, given, so I take again the idea of spins S and interactions J, which are quenched here. But of course, that can be generalized to any problem, as I've shown before. So suppose you have fixed the interactions between your spins, and we like to compute the average value of some quantities, what we call observable, right? So the definition here of the expected value of O given J, and I will use this bracket notation here for that, for the thermal average, is simply that I should sum over all configuration of my spins, the value of the observable in this configuration, and I should weight by the probability of this configuration for my particular set of quench variable, right? And if I go back to the definition of this is the normalization factor times the exponential minus the energy, which is this function of S on J. And of course, I have similar formulas if I want to compute higher moments. For instance, the square moment, there should be just a power 2 to the observable. Wouldn't change much, right? That will in principle depend on my particular set, my particular realization of a J variable, right? So in some examples, actually, you may want to compute the average over your J matrix. And that is all the more true that some quantities actually in the large size limit, and we'll see examples in the next lectures, actually are highly concentrated. They do not depend very much on the particular matrix of interaction you have chosen, but all matrices, or let's say almost all matrices, would actually behave in the same way. They would give the same value to this observable here, right? So it's a kind of self-averageness property or of high concentration property. So in that case, if you want to compute the average value over the J, over the quench disorder here, and I will denote that by the over bar, then what you should do is compute the average value over J of this thermal average. So you should do the average value of this thing, over J, right? And then if you have done that, you have a quantity which depends on S only, and you can compute the sum of S. Obviously, what you see here is that it's a very tough thing to do in general, because you have a dependence on J here, you know, and you have also a dependence on J which is in the normalization factor here. So averaging over quantity which is both at the numerator and denominator can be very difficult in practice. So the first way of seeing the replica method is a trick to put everything at the numerator. So, and this was introduced this way. So the idea is that here we have 1 over z, okay, and 1 over z we can always write as the limit when n goes to 0 of z to the n minus 1. That is for sure is correct, right? So n here is just a real number, which I will send to 0. Now is the first jump. If I consider z to the n minus 1 when n is an integer, then of course, what is z is just the normalization of my distribution here, right? Remember what was the distribution? That's my distribution, okay? So the z is simply the sum over all possible spin configuration of this exponential factor. So I can write the explicit expression for z here. And since I have this is to the power n minus 1, if n is an integer larger or equal to 2, actually, then I will introduce a certain number of copies of my system, and I need 1 for each power of z. So for instance, for n equals 3, that's z to the 2. So I will need a first configuration which I call S2, and a second one which I'll call S3. And I will need to compute the double sum here of exponential minus e of S2j minus e of S3j. And this is formally the same thing as z squared. Is it okay to everybody? Yes? And of course, for any integer n, this is true. Now, what kind of meaning we can give to this when n goes to 0 is another story. But formally, if I forget about this small problem, you can now use this expression here, okay, for z, for 1 over z, sorry, put it back here, and you see that the average value of all double average, thermal average, and quench average is simply the sum, the limit when n goes to 0, of a sum over how many configurations do I have? Well, I have 1 configuration S here in order to compute the average of the observable I am interested in, so O of S. And I have n minus 1 in order to express 1 over z. Okay, so in total I have 1 plus n minus 1, which is n, the total number of replicas of my system. And that should make sense only when n, oh, well, that should make, we are interested in the limit when n goes to 0. Okay, so the interesting thing here is that the quenched average is done only in the exponential factor here. And you see that all the J's, I mean the quenched matrices here, interaction matrices, they are in all the energy function for all the replicas. So is it clear about that? Yes?
So just a quick question. How do you compare this against just taking your z of j and putting a minus log z of j in the exponent, and then Taylor expanding the logarithm to get some kind of powers?
So you can, actually, it's just, okay, here I'm introducing the number of replicas through the average value of some observable, but you can say, okay, I want to compute the average value of a log of z, and you would get also similar things, right?
So they're valid in the same kind of situations?
Okay, so in the regime where the log of z will be concentrated around some average value, right? Then you can compute the log of z using, these usual things. So for instance, you would like to compute the log of the average here, okay? And that you will do by computing exponential, let's say z to the n average, which is exponential n log z, right? And you see when you expand to first order in n, you get the average value of log z. Okay? So it's another way to introduce the small n going to 0 number of replicas.
No, but why can't you just add and subtract 1 inside the logarithm and Taylor expand the logarithm and powers of z and just,
Oh, you want to Taylor expand here log of 1 plus z minus 1?
Yeah, or
Yeah, okay, but we are in a regime where z is actually very far away from 1, right? Z will be typically exponentially large in the size of my system. So it will be exponential capital N times something, right? So we'll be completely out of the radius of convergence of a series and so on. Sorry, I misunderstood your question. Okay. Okay, so we cannot do that. Okay, so is it clear about the approach? So formally, the approach is saying, okay, if I want to compute some quantity, well, I can actually formally write, and so an average of a quantity over the thermal variables and also the quench variable, I can write this as a sum over n copies when n goes to 0 of my system, and I add the average over the quench variables is only in this thing. Okay, so after this formal introduction, let's try to see what that means actually. So again, I'm just copying what was the last line of my previous slide. The average value of O over thermal variables and quench variables is a sum over n copies of O of S times something here. So if we look at this term here, you see, it depends on S, it depends on S2, S3, Sn, and so on. And once I have an average of a J, at least formally, suppose I can do the average, right? J will disappear, and I will get something which I can always write as exponential minus some complicated function of S, S2, S3, and Sn. Okay? And that is an effective energy, which is actually making all my replicas of my copies of my system interacting together, which was not the case here. Here, they don't interact together. They're just independent, right? But once I have average, they do interact. So and I think this is the deep meaning of the approach, so that maybe these three panels are the most important one of the slide. So what we would like to study is the left panel. We have some energy here. Think about it as a loss, right? You would like to minimize. And it depends on maybe on your parameters of your model. And you would like to find the best value, which is the minimum of this function. Problem is that this function is extremely complicated. There might be a lot of local minima and so on, and you don't know how to describe it. So the initial problem is this one configuration in a quench landscape. So what you do, you will replace this problem by, first of all, throwing n configurations in the same landscape, where n is small n, the number of replicas. And they are completely independent, right? So just throwing them, so that means that they are thermalized, they are described by the same probability exponential minus the energy over temperature and so on. So what that means is that if you, for instance, you have a big global, very low global minimum here, by just throwing them randomly and thermalizing, you have a chance that a lot of your n replicas will end up more or less in the same place, right? Just because it's a very good place in the landscape. And maybe the other one will go to slightly higher local minima, but you will find none of them here, right? Because it's very bad, very low probability. Okay, now once you have done that, average over the disorder. So you remove the landscape, right? By averaging over all possible landscape which are defined by all possible J degrees of, the quench degrees of disorder. And what you would get is something which is left here, where there is no landscape anymore, which depends on the quench disorder, but you get only effective interaction between your replicas. And this effective interaction simply because actually there are traces of the fact that the replicas were living in the same landscape before the average. Is it more or less clear? You will see that very clearly on example. Yes?
So is this the fact that the configuration tends to go common, global, flat, minima, whatever, is like this is the concentration effect? Or
Yes, so you will see that in the measure of the similarities between the replicas, which I'm going to introduce. Okay? So this is the very idea of the replica approach. Go from the left panel to the right one. Remove everything which depends on the landscape into an effective theory which tells you how similar are the different replicas because they used to live in the same landscape. Yes?
So you're taking n to some large number of things, of course, where you want to take n to 0. It seems like what your son is saying is that we can calculate this at many different n's, and that will give us like different powers of z, and then we can analytically continue this to get us into 1 over z.
Yeah, you are saying that we can consider different values of n, not n equals 0, I mean.
Like,
yes.
We want many different integer values of n, and then to continue to 0.
Yes, exactly.
But I'm a bit confused. Since I could make, let's say, all the values of n give me an n to 0, and I could have a line or a sine function.
Yes, I agree. I mean, the process, I fully agree. The process of doing this analytical continuation to 0 is very shaky here. I'm not talking about that, right? I'm just saying that, ideally, this is what we would like to do. Then the question is how you do that in practice. So it's going to be very important when we do the calculation and you see how it's done, right? And that there are obviously assumptions to do that. And this assumption can be correct or wrong, and I will try to explain this in the next lectures.
I was just wondering what is the thing we're implicitly assuming in this picture that it applies to?
How we do this n going to 0 limit?
Yeah, that we know it's unique.
Okay, so this is, okay, I'm introducing the overlaps and you will see that. I will come back to that. So just one thing I would like to say is that obviously everything I said here is the n going to 0 limit, but we will see, and I will come back on that tomorrow, that the n not equal to 0 values have also some interest. They can be very interesting because they can allow you to capture very detailed information about the system, which is not transparent here, but you will see that later tomorrow. Okay, so this is a very big idea, and the idea is that actually, since these replicas used to live in the same landscape, they will be attracted by the same place. So we would expect that if you have very deep local minima, global minima, so you would have a high similarity between these replicas, right? Otherwise, it's a very flat landscape. They should be all completely different, for instance. So the measure of the similarities in this last step here should tell us something about the nature of a landscape on the left. Okay, and this is the very idea. And this is different from what people usually do in physics. In physics, people try to understand something about the landscape, usually, by using what is called order parameter. And the order parameter is always a measure of similarity of what you have, your configuration, with respect to some reference state that you know is going to be relevant because you have understood something about the physics of your system at low temperature. So for instance, in a ferromagnet, which is the case where you have all these arrows, these moments pointing up, for instance, at low temperature, the order parameter is simply the dot product between the n-dimensional vector of your spin configuration and this n-dimensional vector of reference state that you know is going to be the correct one at 0 temperature. So, and this dot product is what we call the magnetization. It's just a sum of, so you see it's a dot product of S1, S2, S1, with the vector one, which is pointing all the ones in this Z direction, right, EZ. And this is just the sum of the projection values of the spins along the Z direction. So you have to be a little bit clever if your reference state is not as simple as that one. For instance, in the antiferromagnet, if you do exactly the same thing, that's a bad idea. But you have to do the correct projection of S with respect to your reference state. So that means you have to do the sum of the S with a -1 to the power of where you are on your lattice, right? Which is called a staggered magnetization. And it's always like that, right? And you would think, okay, that's not a problem. If I have a spin glass, I don't know where, there should be some preferred direction at low temperature. So some vector t, and what I should do is compute the projection of S with respect to t, the dot product of S and t. But the problem is that we don't know what t is. We have no idea. It's very hard to find, as I told you. And that can be actually plenty of them. So how do we know that we are actually in some kind of order, which is some kind of vicinity of one of a good T state? So this is where the replica helps, the replica method helps. It's actually, so the idea is that look at that. If you say, okay, I am in this state, if actually my configuration is actually aligned rather well along this reference direction. So an alternative way is to say, okay, now let me take two configurations. So the align is the vertical one, so I had one which was aligned. Now let me take two of them. If one is aligned, then two of them should be aligned. So that means they will be aligned between each other. They will be similar. And this is exactly the idea I was giving before, right? There will be a trace of the fact that there is a preferred direction that I can measure by the similarity between the direction of two configurations. And this is very much the idea. So it's a very simple but beautiful idea. So how can we compute this similarity within the replica approach? So for instance, I can define the overlap, the Edwards Anderson overlap between two configurations S and S prime. So here I have forgotten the vectors. I mean, I'm taking plus or minus one spins, but it doesn't change anything. And in this replica framework, I can compute the thermal average of Q for a given J, which is formally given by this expression here. That's the average of these two copies observable times, weighted by the probability of S and the probability of S prime, which both depends on the quench variable J. Then now, if I want to average this over the disorder, I need to express 1 over z squared with the replica trick. So 1 over z squared, I can write it as z to the n minus 2. So I need n minus 2 copies, right? Just to have one, and when n goes to 0. And then I can write the average value of Q here as the limit when n goes to 0 of, I have a sum over n copies. 2 of them are needed to compute Q, and n minus 1 are needed to compute the normalization here. And then I average over the disorder. So you see, always, it's again and again the same idea. But this is a nice order parameter because it tells you something about the similarities between your configuration. Okay, so I'm almost done with my introduction. So what do we expect for these similarities? So here are 3 landscapes which correspond to 3 cartoons, very much idealized version of a landscape you would expect at different temperatures. So at very high temperature, it should be very flat, right? I mean, the roughness of the landscape is completely erased because everything is divided by 1 over t in the exponent, right? So it's essentially flat. So if you throw replicas here, they will be very far away from each other because you have vectors, and in a very high dimensional space, the vectors which are independent are essentially orthogonal, right? So that means I would expect that this similarity measure, this overlap, is going to be very close to 0. So if I plot the distribution over many replicas of these overlaps, I would expect to find some distribution which is like the green curve here. Oh, sorry, it's not 1/2, it's 0 here, it's a mistake. So they would be very concentrating close to 0, right? And very few copies of configuration would have an overlap close to 1. It would be very unlikely when you throw them at random in a flat landscape. At maybe low temperature, you would start to see some wells here. And now if you throw your configuration, maybe some of them will be in the same well, other one will be in 2 different wells. So maybe you would see some distribution here with Q equal to 0 when they are very far away, Q large when they are close to each other. And that even low temperature, when it's very rough and so on, then maybe the configuration will be very close to each other in the very good spots in the landscapes. And the distribution of Q will be concentrated close to 1, which is the maximal value. So by looking at this histogram of a Q, then we know something about the landscape, right? So this is the order parameter of spin glasses and of this order system that you can actually access to when you do replicas. Okay? So I hope that you get the broad picture, and then we'll see in details when we do the computation how that works. Okay, so I just finished here with these historical notes, just to give you some dates. So the first experimental studies on spin glasses were at the end of the 60s, beginning of the 70s. The Charrington-Karabatic model I mentioned, 74. This solution by Parisi with the replica methods was 79, 80. And actually, the replica method was not invented in that context. It already existed. From my knowledge, it dates back from an application. So there is a beautiful paper by Freeman-Dyson where actually looks at models of random chains of random springs. So imagine you have a system with random springs. You have springs and masses. Okay, and that's on I think boundary periodic boundary condition. Okay, anyway. Okay, so suppose you have some masses here which are random from some distribution, and some stiffness constants here, Ki, which are also random from some distribution, and you ask what are the vibration of this chain here. What is the spectrum of phonons, right? So you start to inject some energy and you get some vibration. Okay, and that can be solved exactly because it's a 1D model without any need for replicas. And in the 60s, actually Mark Katz actually solved again exactly the same model with replicas, right? But that was more or less a kind of exercise. It didn't bring new insight about the physics of this problem. So I think the big change here in the 80s is that replicas were actually useful and completely different solution appeared and a new physics appeared. And it turned out it was very hard to understand this physics. And there was a lot of contribution, in particular by Mark and collaborators, in order to understand Parisi's solution. And the mathematical proofs of the exactness of the solution under the exactness of the interpretation of solution that come from the 2000 and still going on. But in parallel, and this is what we are interested in here, there were many applications to neuroscience, to a random combinatorial optimization problem, to supervised learning and supervised learning in the 80s and going on in the 90s also. Okay, so I think I'm more or less done with my introduction. So I hope you get some flavor of the technique if you have never heard about it. And then I would like to go to the solution of, so I have 45 minutes, on a very simple speed model that we can do without replicas. And tomorrow we will solve exactly the same model with replicas. Is that okay? Okay. Thank you.
Can I ask a question?
Sure.
Yeah, so often I held this issue that